Welcome back. Let's talk about the geometrical isomerism. For geometrical isomerism to be observed, following conditions must be satisfied. The first condition is there must be a restricted rotation about carbon-carbon bonds. The second condition is the two groups or electron densities attached to each restricted carbon atom must be different. And the third condition is the areal distance between same groups or same priority groups must also be different. Once the two molecules having same molecular formula, same structural formula, but they obey these conditions also, they are said to be geometrical isomers, and the phenomenon is called as geometrical isomerism. Now let's identify which molecules can obey these three conditions. So we have alkenes. As you see, the two molecules are having same molecular formula and structural formula, and the double bond between two carbon atoms is restricted because it's formed by the lateral overlapping of two p orbitals. If you begin to rotate one, the pi bond will break, hence the rotation is restricted. The first condition is satisfied. Next, if you see to the each restricted carbon, there are two different groups attached. One is methyl and next is hydrogen. So the second condition is also satisfied. And the third is that if you see the areal distance between two similar groups, that is two methyls, in the first case and in the second case, it's different. So all the three conditions are satisfied. So these are said to be geometrical isomers of each other. Now, how can we designate these isomers? For that, we have a nomenclature that says if two same groups lie on same side, then it's a cis isomer, but if they lie on opposite side, then it's a trans isomer. In the first case, the two methyl groups or the two hydrogen groups lie on the same side, so it's a cis isomer, while as in the next, the two methyls or the two hydrogens lie opposite to each other, so it's a trans isomer. Let's take one more example. In these two cases, there are two double bonds as you see, the first one and the second one. Clearly, there will be restricted rotation about each double bond, but if you see, the second condition is not satisfied in the first restricted center because of the two similar groups, that is hydrogens attached to a restricted carbon, but nevertheless there are two different groups attached to the second double bond. As you see, on one restricted carbon there is methyl and hydrogen, on the another there is one methyl and one a vinyl group. So as the second condition is also satisfied, and you can see the areal distance between two methyls in the first case and in the second, it's different, hence they are geometrical isomers of each other. The first one will obviously be a cis isomer, while the second one will be a trans isomer. Taking one more example, in this case we have fluorine and chlorine on one restricted carbon, while bromine and iodine on the another restricted carbon. So clearly cis-trans nomenclature no longer applies here. For this particular case, Kahn-Ingold Prelog system has been used, which says instead of cis-trans notation, E and Z nomenclature is used. As per CIP system, atoms or groups are given priority based on atomic masses. Then, if same priority groups lie on same side, it's a Z isomer, which comes from zusammen, means together, otherwise E isomer, which comes from antigen, means opposite. So as you see, chlorine is having more mass than fluorine. Obviously chlorine will get priority first and fluorine will get priority second. Similarly, on another side, iodine will get priority first because of larger mass, while as bromine will get priority second. Now as you see, the same priority groups lie on same side, so it's a Z isomer, while as in the next case it's an E isomer. This was the talk of alkenes. Now let's identify one more case, that's oximes. Oximes are the compounds having this functionality, we have C double bond NOH. So N contains a lone pair and a hydroxyl group. Now, as you see the two isomers, there's a double bond, so there's a restricted rotation. We have on nitrogen one hydroxyl and one a lone pair electron density, so it's a different. And on the other side, we have one hydrogen and one methyl, so each restricted center contains two different groups or electron densities attached. The second condition is satisfied, and now the aerial distance, if you see OH and H, is different from the same atoms or groups when they are opposite to each other. Clearly, as all the three conditions are satisfied, they will definitely be geometrical isomers. Now, how are they designated? Before that, point to be noted is, as you see, we have one methyl and one hydrogen attached to the doubly bonded carbon or the restricted carbon, so it's called as aldoxym. Now, they are designated as either syn or anti, and this is given with respect to the OH group. With respect to that OH group, the hydrogen is on the same side, so it becomes a syn isomer, while as in the another case, with respect to OH group, it's on the opposite side, so it's an anti-isomer. Now, we have two more examples. In this case, the carbon atom is attached to two alkyl groups. For that reason, they are called ketoxins. And again, all the conditions are satisfied, so they are geometrical isomers. The first one is syn-ethyl or anti-methyl, while the second one will be syn-methyl or anti-ethyl, because we are giving the nomenclature with respect to the OH group attached to nitrogen atom. Next, we have azo compounds. Azo compounds are the compounds containing N double bond N. Now, as you see the two examples over here, we have nitrogen double bond nitrogen, so there is obviously a restricted rotation. Next, each nitrogen contains one methyl and one electron density, so it's different. As you see, the two methyls are on the same side, so the first isomer will be syn, while as the another will be an anti-isomer. Next, we have cycloalkanes. Cyclopropane, as you see, there is obviously a restricted rotation about carbon-carbon bonds because it can otherwise break the ring. And moreover, in addition to the three conditions talked about earlier, there is one more condition in case of cycloalkanes is the carbon atom to which the two different groups will be attached must be sp3 hybridized. Now you can see in cyclopropane there are three restricted carbon atoms. The two restricted carbons do contain different groups. On one side it's hydrogen and methyl, on the another it's hydrogen and methyl again. Now as you see, the two methyl are on the same side, so it's a cis isomer. In the next case it will be a trans isomer. We have one more example, that is of cyclopentane. There are 5 carbon atoms that are restricted. Hence, to the 2 carbons, as you see, there are 2 different groups attached. Second condition is satisfied. Moreover, there will be the aerial distance also different. And one important condition in cycloalkanes is the carbon atom to which the different groups are attached must be sp3, and it is. So the first molecule will be a cis isomer, while the another will be a trans isomer. In the next case, as you see, there is a ring and the double bond. Clearly, there will be a restricted rotation about carbon-carbon double bond and that of the ring. So, double bond designated as 2 will not be a stereocenter because there are 2 similar groups attached to the restricted carbon. As you see, the 2 hydrogens attached to the restricted carbon, and looking at the ring designated as 1, there is nevertheless the 2 different groups attached to one restricted carbon, and this carbon is nevertheless sp3, but on the other side it's a double bond, that's an sp2 carbon, so it doesn't obey the conditions. So this does not show geometrical isomerism as there are no stereocenters possible. In contrast, talking about the next case, as you see, there is again a double bond and a ring. So both or none or one among them can be the stereocenter. Now identifying first of all the ring. Ring do contain 2 different groups on one carbon, but on the another there is an sp2 carbon center, so ring no longer qualifies to be a stereocenter, while as the double bond do, as designated by star, because on one restricted carbon there is one methyl and one hydrogen atom, that is two different groups are attached. On the other side we also have the two different electron densities attached. So because of this double bond, as it becomes a stereocenter, it will show geometrical isomerism. Now given the priority, the upper ring portion will get priority 1 because of larger mass, while the lower ring portion will get priority second. Similarly, methyl will get priority first because of larger mass, and hydrogen will get priority second. So as the same priority groups lie on the same side, so it's a Z isomer, while as the next one will obviously be an E isomer. Next we have cycloalkenes. Cycloalkenes do not usually show geometrical isomerism due to sp2 hybridized carbon, which would not allow trans isomer to form. So as you look to this molecule, there is a double bond in the ring, so it's a cyclohexene actually. Two hydrogens are on the same side, so it's a cis isomer, but trans isomer cannot exist because for that one of the hydrogens must be opposite to that of the next hydrogen, and which is not possible as the angle is 120 degree, which is because of the sp2 hybridized nature of carbon. However, geometrical isomerism has been found to exist if the number of carbon atoms are greater than 7. As you see, in these two cases we have 10 carbons in it. So in the first case, the two hydrogens are on the same side, so it becomes a cis isomer, while as in the next, the two hydrogens are on the opposite side, so it's a trans isomer. And this arises because of large number of carbon atoms present. They can adopt such configurations and hence can make the existence of geometrical isomers. Next we have allenes. Allenes are actually dienes with consecutive double bonds. As you see, these are the two molecules, and there are two double bonds which are consecutive to each other, and there will obviously be a restricted rotation about the double bonds. And as you see, the restricted carbons do contain two different groups, so we expect them that these molecules should be geometrical isomers, but actually they are not. The reason is the two restricted carbons do not lie on the same plane, they actually lie in two different planes, because of which the areal distance between the similar groups in one molecule is same as that in the second molecule, so it violates the third condition. Thus allenes do not show geometrical isomerism. Talking about spiral compounds, they do show geometrical isomerism provided the number of spiral rings are odd. As you see, we have 3 spiral rings in these molecules. First spiral ring, that is cyclobutane, and the third one lie in the same plane, and they do have different groups attached. So similar groups are on the same side, it becomes a cis isomer, while as in the next case it becomes a trans isomer. Here in this case the areal distance is different, but if you take the spiral rings even, the first ring will be in one plane, while as the last one will be actually in the different plane, making the areal distance similar. Just like allenes, at that time it will not show geometrical isomerism. I hope you understand this. This was all about geometrical isomerism. If you like this, please do share and subscribe. Thank you.